Hello, everyone. Good afternoon here from Chile, and good morning over there in Auckland, New Zealand. Today we are here with Professor Laurie Wesley. Professor Wesley is a professor emeritus from the University of Auckland. Hello, Professor. Good morning for you. How are you?
And good morning to you. I'm very well, thank you.
How is everything in New Zealand?
In New Zealand, we are just saying goodbye to summer, and like you will be so also. It's starting to feel a bit cold, and the sun has been shining, but we've had a lot of rain during the summer. In fact, we didn't really have a summer, it just rained all the time. But now in the autumn, we're having some sunshine.
Same here. It's the same here. It's exactly the same here.
Good.
So, Professor, I have some questions for you before we start.
Sure.
I wanted to ask you, how did you become a geotechnical engineer? How was your career, your full career, since the early beginnings to these days?
When I graduated, there was an arrangement between the New Zealand government and the Indonesian government. We could travel to Indonesia at the expense of the New Zealand government, and then we were employed by the Indonesian government. They were quite short of staff of various sorts. So when I first went to Indonesia under that scheme, they sent me up to Bandung, which had quite a well-established soil mechanics and materials testing laboratories. And they were very short of staff, so they appreciated me coming. Of course, I had to learn Indonesian very quickly because hardly any Indonesians could speak English, so I had to learn my Indonesian very quickly. You might be interested to know too that when I joined the institute in Bandung, they had 10 CPT apparatuses, the Dutch cone penetrometer test, and they had two 10-ton ones, and Indonesia was the only country apart from Holland that was using the CPT test. So I began my career learning all about the CPT test.
Oh,
so that's how it started. It was sort of by accident because I went to Indonesia not knowing where they would send me, but they sent me up to Bandung to the laboratory because it was short staff. So I worked there for 4 years. I came back and worked in New Zealand for another 5 years, and then I went back to Indonesia again for another 4 years. That's really why, well, to go back a step, the reason I got invited to come to Indonesia was because from my experience in Indonesia with andesitic volcanoes and volcanic soils, I wrote some papers. And I know that you have similar soils in Chile, and I think some of Ramon's students were studying them and they came across my papers. And so I was invited to Chile by the University of Chile to talk about allophane clays and volcanic clays. So that's how it all started, my involvement with Indonesia.
I see. I see. And was right there around that time that you entered in contact with Professor Bishop?
I was sent to London by the New Zealand Ministry of Works in 1964 to attend the 1-year master's course. So I did that. Then I came back and I worked in New Zealand for another 3 years. Then I worked in Indonesia for another 4 years. Then I decided I would quite like to do a PhD. So I wrote to Bishop. He already knew me from when I was doing the master's course. So I wrote to Bishop to ask whether he would accept me as a PhD student and could he provide any financial assistance. And I got an immediate reply that he would be very pleased to employ me, and he had a research grant and he could employ me for 3 years, during which time I would do my PhD. So that was how I started on that. And many years later, I was leaned on, is the term we use. I was pressed to write a biography of Bishop because they thought I was in a position to understand the man, having done his master's course and his PhD course. So
Because
that was in
you were a
19.
friend of Dr. Bishop also, right? You were a friend.
Yes, because I was an older student. You see, I was an older student when I did the master's course. I had already had about 5 or 6 years experience. When I did the PhD course, I did it between the ages of 37 and 40. So I was quite experienced by that time. Yeah, we got along together very well, Bishop and I.
I see.
And shall I take this opportunity to show you that I wrote
The book,
the biography of Bishop, that book
The Bishop
there,
Method.
The Bishop Method, and alongside it, I got the publisher to also publish a book of his best papers. So there's a biography and a set of Bishop's papers as well, published at the same time. All right.
Very nice. Very, very nice. Very, very nice, Professor.
It was much more fun writing a biography of Bishop than writing technical papers. It was really
definitely.
wonderful
I bet.
experience.
I bet you enjoyed
Exactly.
that way more.
That's
Okay.
right. That's right.
Okay. So, Professor, well, thank you very much for making time in your schedule to share with us the life of Professor Bishop, what you learned from him, and many other details that probably many people don't know about this legendary figure of our field, right? Geotechnical engineering. So thank you very much again for taking the time.
Sure.
We really appreciate it. And
Pleasure.
I will share
No
the
problem.
screen so you can start presenting on the life of Dr. Bishop. And I will turn off my camera so you can have the full stage, okay? Thank you very much again, Professor.
Thank you. Perfect. Perfect. Now I just need to turn this here off. Now, can everybody hear that and see it now?
Showing.
Good. The copy there is from a page of Bishop Terzagi's book, where he is describing the principle of effective stress. It's from Terzagi's book, Theoretical Soil Mechanics, which was published in 1943. And incidentally, 1943 was the year that Bishop began his career. He started working for the London Metropolitan Water Board in 1943, the same year that Bishop's Terzagi's book, the first significant soil mechanics book on the field. Okay, next one. Now I'll read this out. Terzaghi is the undisputed founder or father of modern soil mechanics. The publication in 1925 of his book in German, Mechanik, is regarded as the birth date of soil mechanics. Terzaghi was born in 1883 in Prague into an Austrian family. His father was an officer in the Austrian army stationed in Prague at that time. He did a degree in mechanical engineering, but became interested in geology and eventually settled for a career as a civil engineer. His work career involved times in Vienna, Istanbul, America, back to Vienna, and finally settling in America. He died in 1963. And by the way, he was a very keen geologist and always emphasized the importance of geology for engineers. Next. Next slide. Terzaghi discovered and explained that when a force, pressure, or stress is applied to a soil, it will normally be resisted by both the soil particles and the water that occupies the space between the particles. And as you know, the principle is expressed in a very simple equation. The effective stress is the total stress minus the pore pressure. And Terzaghi maintained quickly that change in soil volume or in strength only occurs as a result of a change in effective stress, not as a change in total stress. Next. Terzaghi adopted the basic equation for shear strength of soils as that was established by Coulomb with studies of sand. Coulomb assumed that the value of sigma was the direct normal stress on the soil and that the soil behaved like a dry sand. He was unaware of any issues influencing that assumption. Terzaghi recognized that the value of sigma could be either total or effective stress. He also understood that the best way to investigate how soils responded to applied stresses was by undertaking triaxial tests. That's because in the triaxial test, he had control of both the horizontal and the vertical stress. So he adopted that as it became the standard means for measuring the shear strength of soils. However, Terzaghi did not get as far as establishing a sound theoretical basis for applying the above equation and the results of triaxial tests to practical situations. Move on. Next slide. Next slide. And this is a quote from his book, Theoretical Soil Mechanics. For these reasons, the data required for making a stability computation pertaining to clays can at present be obtained only by means of the following purely empirical procedure. We test the clay in the laboratory under conditions of pressure and drainage, similar to those under which the shear failure is likely to occur in the field, and we introduce values of C and phi into our equations. And this is still Terzaghi. It is obvious that the success of this procedure depends chiefly on the degree to which the experimenter has succeeded in imitating field conditions. And the important point, and this is where Bishop comes in, Terzaghi established the principle of effective stress, but failed to arrive at a rigorous method for applying it to the analysis of stability of situations, especially slope stability. So Terzaghi's book and some various published papers were all that Bishop really had to start his career with. And he very quickly realized the challenge was to establish how you apply the results of triaxial tests to field situations. Next one. This is Terzaghi's achievements were the result of unrelenting examination of how soils behave, primarily from careful experiments in the field, but assisted by laboratory experiments. And he developed theories to explain that behavior. Next slide. This is what I've said. Terzaghi's book, Theoretical Soil Mechanics, was published in 1943, and that was the year when Alan Wilford Bishop joined the Metropolitan Water Board, working closely with the soil mechanics group at the British Building Research Station. And the leader of the group at the British Building Research Station was Skempton. So that's how they met, actually, that Bishop was working with the Metropolitan Water Board, but he became aware of the work that Skempton was doing, and they worked together to solve some of the practical questions at the time. Okay, next slide. This is a tribute that Skempton paid to Bishop after Bishop died. Bishop died young at the age of 68. This is Skempton's statement. It was a great privilege and the best of good luck to be associated for nearly 40 years with one of the finest intellects in our subject. In no respect was his intellectual power seen more clearly than his continued study of Terzaghi's principle of effective stress and its application to all branches of geotechnical engineering. His work in this field brought about a highly beneficial revolution in soil mechanics. Although reserved in a manner compatible with his Quaker faith, he appreciated a good sense of humor. He was loved and respected by his numerous students who came from all parts of the world. Through them and the strict but friendly criticism of his colleagues' work and his own important contributions, he exerted a unique influence. Next slide. You needn't take too much notice of this, but the important dates actually are 1936. They were building a big additional reservoir for the London Metropolitan Water Board, and they had a major failure of one of the embankments there. Oh, sorry, that was the first international. The first international conference was in Harvard in 1936, organized largely by Casagrande. This is where the major failure occurred here. And it was in 1943 that Bishop joined the Water Board and became aware of the failure of the banks at the Chingford Reservoir, which was what Skempton was involved with. And so he studied, of course, all of the papers available to him. They engaged Terzaghi to write a report on the failure of the Chingford Reservoir. And in fact, I have a copy of the report that Terzaghi wrote on that. And so Bishop set out to try and solve this problem of how you apply shear strength to the stability of slopes. And the most important paper that Bishop ever wrote was written in 1960. By about 1953 or 54, Bishop had sorted out how you should apply the results of triaxial tests to stability analysis. He published a very important paper in 1960 at an ASCE specialty conference, and it was co-authored with Bjerrum, who was the leader of the Norwegian Geotechnical Institute. And that paper set out very clearly how you should apply either a total stress analysis or an effective stress analysis. So it really solved the question which Terzaghi had failed to solve. Okay, next slide. Bishop's early years, a major slip occurred in 1937 during construction of an embankment for the new Chingford Reservoir. The thorough investigation of this slip is regarded as the birth of soil mechanics in England. I've already said that, but I'll read it. Bishop in 1943 joined a small soil mechanics group at the Building Research Station. He was employed actually by the Metropolitan Water Board, but he was working with the BRS that was responsible for investigating the cause of the failure and remedial measures. It also worked on modification of the design of a second reservoir, taking account of the lessons learned from the Chingford failure. So Bishop was very quickly involved with the issue of the stability of slopes. Bishop faced the issue left unresolved by Terzaghi, a rational way of using the results of triaxial tests for analyzing practical stability situations. Next. Bishop was the ideal person to take up this challenge for several reasons. He was a very practical man. He began work as an engineer at the Metropolitan Water Board, where his first task was the design of a water-retaining embankment. His first job made him realize how important the issue of soil shear strength was for the safe design of reservoir embankments. And he was fascinated by Terzaghi's effective stress concept and its formulation in a very simple equation. And Bishop had a very sharp mind, essential for the development of theory. And also he was a very capable designer. He knew how to design laboratory equipment. In fact, when he was still in his school years, he had persuaded his father to allow him to use part of the house as a workshop. So he already had his own workshop before he went to the University of Cambridge, where he took various subjects to get a degree there. Okay, next one now. A note on the Bishop method. Bishop is best known for his method of slip circle analysis. However, in the Bishop obituary by Angus Skinner, published in Geotechnic, we find these words, theory and practice, welded together by continually checking one against the other. This was the formula used so successfully by Bishop. This gives us a much broader understanding of the term, the Bishop method. People think of the Bishop method as the method of slope stability, but Bishop's method of operating by always checking theoretical things in practice was the was what made him very successful. As I've said here, Bishop was a very practical man. His interest was in whatever helped solve practical problems. He had little or no interest in theory that was of no practical value. For this reason, he had a very negative view of critical state soil mechanics. He worked on three fronts: the development of theory, the creation of laboratory equipment, and particularly field observation. He always emphasized field observation and the importance of geology. Next slide. Now, this actually is Bishop's first triaxial apparatus. I think it was the first triaxial apparatus operating in England, which he invented. It's quite sophisticated. It's got a, I visited it when I was in London going through the archives of Imperial College. They keep all of Bishop's papers and things there. And I also visited the Metropolitan Water Board. It has a mechanical means of recording in graphical form the results of a test. There was no electronic stuff like that available, but it had a mechanical system and a rotating piece of graph paper, which gave you the graph here. It also had a rotating bush at the top here to get rid of friction between the bearing and the vertical rod that was leaning down on the top of the soil. So it was very clever design, typical of Bishop. Next. That was what I designed when I was at Imperial College. Bishop wanted to do tests on soft clay, which were stress controlled, not strain controlled. I went to Imperial College to do a PhD with a very firm idea. I wasn't going to spend half my time designing the equipment like a lot of PhD students do, and then they have hardly any time to do testing. I was determined to make use of whatever was there. But Bishop said, he told me what he wanted. He wanted tests done with control over both the vertical stress and the horizontal stress. He told me to look around the laboratory and see if there was anything suitable. Obviously, to do that, I think you have to, or at that time, you had to have a hydraulic system because you could more easily control the pressure on fluids than you could on solid pieces of equipment. Anyhow, I tried to devise a system for applying the load, the vertical load, as a controlled load or controlled stress. But my designs weren't very satisfactory to myself or to Bishop. So then I changed it around so that the vertical load now comes from the base. The sample sits on a pedestal, and there is a rod which takes you right down to the bottom. And at the bottom there is a hydraulic chamber. So you have these two controls, one controlling the cell pressure, the other one controlling the vertical load by increasing or decreasing the pressure in the cell at the load. And I was a bit fortunate, actually. Bishop thought it was a really good design and wrote a paper on it, and it got manufactured by Wickham Farris, I think, on a company called, I just forget, doesn't matter, but it quickly became available commercially. And it is still produced, actually, and sold commercially. Okay, carry on. Yeah, that's what I've already said. During the 1950s, Bishop established the theoretical understanding of the shear strength of clays. The understanding is described in detail in the 1960 paper with the relevance of the triaxial test to the solution of stability problems, published by the ASCE Research Conference on the Shear Strength of Cohesive Soils, held in Boulder, 1960. That paper was undoubtedly Bishop's most important paper, even though he is best known for his method of slope stability analysis, published in 1954. Carry on. Next slide. The principle of effective stress, I don't need to run through this. There's an expression there for the volume change, and there's an expression there for the shear strength. Note, the equation C equals sigma tan phi is meaningless without defining the type of stress for sigma and the way it is measured. In other words, you must state whether your sigma is a total stress or an effective stress for that expression to have any meaning. Next picture. Next slide. The shear strength determining determined using the above equation is the strength in terms of effective stress. To use the equation, it is necessary to know the value of the soil parameters, C and phi, and the pore pressure U. That's a very basic statement about analysis in terms of effective stress, what you need to know. There's a second way of measuring the shear strength. That is by directly measuring it without allowing any change in its water content. For fully saturated soils, this means that no change in effective stress is occurring, and as you are probably quite familiar, this strength is thus a constant known as the undrained shear strength. Some people call it the cohesion, but that's not a sound term at all. And Bishop I think Bishop invented the term, the undrained shear strength, denoted by CU or SU. Measuring SU can be done in several ways, and of course is much easier to measure than C prime and phi prime, the effective strength parameters. Next slide. Yeah, I think you are all familiar with that diagram there. You can measure the effective stress failure line, which gives you the two parameters, the C and the phi, or you can do tests, which will give you a total stress, or if you are doing triaxial tests and you are doing them undrained, the result you get is independent of the cell pressure, because each time you raise the cell pressure, you also raise the pore pressure in the sample, and the effective strength stays the same. So then you can plot a line of samples like that where no change has occurred. The undrained triaxial test, a graphical illustration of the principle of effective stress and undrained behavior, is conditional on two factors. One is that the soil sample is fully saturated, and the second one is that the test is undrained. And some people seem to think that that total stress failure line is something you get from clay, and the one with the effective stress is something you get with sand. That is not the case. You will get an identical result provided the material satisfies those two conditions, whether it is a clay or whether it is a sand. If the sample is fully saturated and the test is undrained, you will have no change in the strength with increasing the cell pressure. The increase in the cell pressure is always resisted by the pore water within the soil particles. However, the undrained strength is only of practical value in the case of clays. I don't think it has much relevance to sand. Okay, the next picture, next slide. Bishop established that the geotechnical engineer normally has a choice of two methods for analyzing a stability situation: an undrained or total stress analysis based on the undrained shear strength. Skempton always called it the phi equals naught method, which was sort of valid in a way, but Bishop's statement that it is a method, it is a total stress method of analysis rather than a phi equals naught method, but it does give you the value that the apparent value of phi is 0. So you've got that as one method, and you've got an analysis in terms of effective stress based on the effective stress parameters. The latter, you'll find the latter is sometimes called a drain analysis, but that's not a sensible term. Analysis in terms of effective stress makes no assumption about whether the failure will be drained or undrained, and an undrained situation can be analysed in terms of effective stress. There's nothing to stop you from analysing an undrained situation, provided you know C phi and the value of the pore pressure, which in many cases is the more difficult one to determine. Okay, next slide. Yeah, Bishop stated that for most stability situations, there are two cases to consider: the end of construction or immediate case. Stability in this case can be estimated using a total stress analysis based on the assumption that the clay is of very low permeability and the undrained strength does not change during construction, and the long-term case, which applies when sufficient time has passed for pore pressures to reach their equilibrium steady state. Stability in this case is normally determined using an effective stress analysis but there are cases where a total stress analysis may be appropriate, taking into account the change in undrained strength that may have already occurred. Okay, next slide. Yeah, this is just explaining why you can always design your foundations on clay using the undrained shear strength, because when you build on a building, it applies a load to it, and the pore pressure beneath it will rise and it will slowly drain away. So in that case on the left, the strength of the soil will steadily increase with time. So you are perfectly sound in determining the shear strength or the bearing capacity using the undrained strength of the material. But the opposite is the case on the right-hand side. That when you do an excavation, it will take off the load acting on the soil, and it will tend to lower, or it won't, it will lower the pore pressures beneath if the behavior is still undrained. But because the pore pressures in anywhere where you have taken the load off are now lower than those elsewhere, water will start to flow towards the excavation. If that happens, the strength will steadily decrease. So you can't estimate the stability of slopes or cut slopes using a total stress analysis, because in that case, the undrained shear strength will steadily decrease with time. So that's just a simple explanation of the basis or the reason why we can use the undrained strength for determining bearing capacity, but we can't use it for estimating the long-term stability of cut slopes. Okay, next slide. For made slopes, such as cut slopes in original ground or embankment, it is generally necessary to make two estimates of stability: the situation at the end of construction and the long-term situation. The estimates are likely to be different because the pore pressure state will probably change with time and thus produce different values of safety factor. Yeah, carry on, next slide. Soil, this is just an important point. Soil will behave in an undrained state in either of the following situations: when the water is unable to flow in or out of the soil because all boundaries are impermeable, which is the case in an undrained triaxial test. So that is one case where the behavior will be undrained. The second one is when the soil permeability is very low and the loads or stresses are applied rapidly, as for example, when an excavation is made rapidly or a storage tank is filled quickly in low permeability. So in that case, it is behaving in an undrained manner simply because there isn't time for the pore pressure to get out. Whereas in the first case, it can't get out because of all the outlets, none are available. Next slide. We will now consider some practical situations and look at the question, why do we use, I partly answered this already, why do we use a total stress approach using the undrained shear strength in some situations and an effective stress approach using the effective stress parameters in other situations? I partly answered that. Carry on. Next slide. Bearing capacity. The bearing capacity is almost always based on the undrained shear strength SU for two reasons. The SU is the initial strength and it will increase with time, so the approach is safe. It is also much easier to measure SU than the value of C dashed, phi dashed, and U, the pore pressure. All three would be needed to make an estimate using an effective stress method. In other words, if you put that building there on and try to on a clay and try to estimate the stability situation, you need to know C and phi and the pore pressure. The C and phi you can measure in the laboratory, but the value of U will be the value of the pore pressure that was there at the start, plus whatever additional increase in pore pressure occurs when you build the building, which will be variable. It will be one value near the edges and another value at the middle. So trying to use an effective stress analysis to come up with the bend capacity of a clay is not an easy task. Yeah, the other situation, of course, where those are just the three possible foundations. Oh, sorry about that. That writing underneath. That writing is Indonesian. I must have prepared this when I was teaching there. But the same issue arises whether you're building a building, filling a tank, or building an embankment. It's always easier to estimate the bearing capacity using the undrained shear strengths. Right, I'll carry on to the next one. Yeah, now the slope stability situation, it's almost always done using an effective stress analysis. The advantages of an effective stress analysis are, I think, well, especially theoretically, the safety factor is much more reliable than from a total stress analysis. Perhaps I've overworded that. It's probably more reliable, but the effective stresses enable the seepage state to be included and its influence on the safety factor investigated. And I think you're all sufficiently familiar with that you need to know those three. And in general, you can make some assumptions about a phreatic surface, or if you don't know what the actual value is, you can make some assumptions about it. But the pore pressure will probably be the least certain parameter that you use when you do a analysis of the stability of a slope. Righto, next slide. Yeah, just looking at these, designers will be using different approaches, but for the design of a retaining wall, a total stress analysis is likely to give an unsafe answer. A long-term analysis using effective stress, I think, gives a more reliable answer. I think that would apply to any situation, but again, looking at those other situations there, the stress that eventually ends up acting on the wall is very dependent on the way you do the building. If you look at the first one here, you're probably going to make an excavation and have a temporary cut there, and then come along and fill it up with backfill. So you immediately got two possible, well, you've got a whole range of possible failure planes, one of which will be in the backfill and one will be in the natural ground. It's probable that the values of C and phi in the natural ground are less than those in the backfill. You'll tend to choose some nice granular backfill with quite high values of phi. But again, I think you would always do an analysis in terms of the effective strength parameters rather than using the undrained strength. Again, on the next one over here too, if you do what we call them a soldier pile walls, where you put your piles in generally board, and then you put them in as a row, and then you do your excavation so that initially you're using the pile itself to restrain the soil, but you have your piles sufficiently close together that you can put horizontal timbers or precast concrete ones in between, and then you fill in the gap with soil or drainage material. So again, it's rather dependent on how you're building it and the extent to which you compact your backfill up against the wall. So you need to be aware of those situations. But again, as I say here, and again, when you're building and putting your anchors in, it depends on the way in which you put your anchors and the amount of stress you put in them when you actually install them and tighten them. And similarly with the diaphragm wall, it looks there when you build from the top down, you put your diaphragm wall in, and then you put your floors in and do your excavation. So the load is steadily coming onto the each floor as you do the excavation, but it doesn't mean you're going to end up with a nice tidy stress state at the back of the wall. It will be quite different for that. You can just think about it as you carry the excavation out. When you put your top floor slab in and you excavate down, as you carry out that excavation, load is going to come onto the top floor. And as you keep coming on down, the load is going to come onto the upper floors. So it's not possible that you're going to have a nice triangular stress distribution as you put the floors in, because you're transferring load from the lower level to the higher level as the excavation takes place. So you need to be aware of that. Okay, on to the next picture. Compacted embankment on the soft clay. Now this was Bishop's project that he was involved with, that I did my testing for my PhD. Just going back a little bit in history, in 1953 there was an enormous storm and high tide in the North Sea, and it swept it down through the North Sea along the coast of Holland and along the coast of England. And in Holland, it overtopped a lot of their dikes, and a lot of land was covered. And in England, it swept up the English Channel and swept across an area called I can't forget it, an island, but about 50 people were drowned in England. So the response to this was to raise the height of the stop banks or the embankments. So that was why Bishop had the research grant. It was to do an investigation of the shear strength properties of the soft clay. That was what my PhD was worked out. So just some notes about a compacted embankment on soft clay. If the embankment is made of granular material, the analysis should use for the clay layer underneath the undrained shear strength, and for the sand, the effective stress friction angle. If the embankment is made of clay, the analysis should use for both materials the undrained shear strength. And often it is the case when you are building an embankment on soft clay that you will need to allow time for the soft clay to consolidate and increase in strength. If staged construction is necessary, which is often the case, necessary to allow time for consolidation, the increase in the undrained shear strength should be measured and used in the stability analysis. Now, a lot of people tend to rely on empirical methods or very vague methods, or they assume that if they measure the settlement, it's indicating that the material is behaving as expected and you're getting the increase in the undrained strength. My own view is that that's not a very safe way to approach it. If it really is critical, and it often could be critical, to know just how great an increase in undrained strength you're getting, my view is you should do some careful CPT tests of the clay before you put the material on. And then if you want to check whether you're getting that increase in undrained strength, you should come back. You may have to drill through the fill and put a CP test down again, so you can then check whether you are getting the increase in strength that you assumed you would get by using a staged construction method. Okay, let's on to the next slide. Questions that arise regarding analysis in terms of total stress and in terms of effective stress. Should both methods give the same answer, e.g. the same safety factor? If the answers are different, which gives the correct answer? On to the next picture. Yeah, let's just think about this. We're thinking about the shear strength on a plane, like in the top one there, that brown line there, where we've got a possible failure occurring on that plane. We can determine the C and the phi value, and we can measure the pore pressures. And so we can do a set of triaxial tests and establish the Moore-Coulomb failure line there. So with that information above, we can plot in the value of the effective stress. And if you look at the bottom there, the green line coming up, that's the effective stress that we have estimated is the effective stress on some plane in the field, or particularly on a circular surface on which a failure might occur. So that's the strength you would use or it's the strength that you would think was justified because you're putting into the picture at the bottom, you're putting in the effective stress in the field, and you're reading off on that line what the effective strength would be. But you must remember that when you did your triaxial test, you created an increase in the pore pressure. You can't do a undrained triaxial test without the pore pressure increasing or decreasing. And most people measure the CN5 values during consolidated undrained tests. So even if you set up your test with the same effective stresses acting on it as in the field, as you do the test, you will increase the pore pressure and you will get a different value of strength. So while you may think you're justified in just measuring the C and the phi, knowing what the value of the effective stress is on that plane, and as I said, you in the picture, you draw that green line up to the point A, and that's the strength that you will be getting in whatever slip circle analysis you use. But in fact, when you actually do the test, you create another value of pore pressure, that pore pressure there used. So in fact, that value is different from the strength that you had in the field. It's just a point to be aware of as to why an analysis in terms of effective strength gives you a different value from an analysis in terms of total strength. You can go away and think about that. I think my reasoning is correct, but you might like to challenge it. Okay, let's go on to the next picture. Yeah, this is an assumed situation. The red line is an assumed possible failure line, all right? That red line there. Now, in your analysis, what I'm plotting with those arrows there are the values of shear strength being used in the analysis. If you're using the undrained strength, in all probability, you will be assigning a uniform value all the way around that red line. So you would have that graph that I've given of the undrained shear strength value there, uniform all the way around there, provided your clay is uniform. And that's, I think, what people would do if they were using an undrained analysis. But if you were doing it in terms of effective stress, then your analysis would be reading off the effective stress on that red line, which would be very little at each end. So you would be starting at almost a zero value at each end. And as the effective stress along that line increases, you would have an increase. So you're actually using quite different values of your strength parameter in the stability analysis. Strength along a potential slip surface using a total stress and an effective stress is quite different. So that actually answers the question as to why you're not going to get the same answer from an effective stress analysis as from a total stress analysis. Next picture, we're just about coming to the end, I think. Yes, this is just explaining what happens when you make an excavation into clay. And this was an issue that was a big issue actually in the early years of soil mechanics. And the issue was that they had built their railway systems, particularly in London and in other areas, in a lot of cases through heavily over-consolidated sedimentary clays. And their cuttings were staying stable for many years, sometimes decades, and then they would fail. And if you've ever read Skempton's Rankin lecture, he has a concept there whereby, because these clays are fissured clays, their strength was steadily decreasing with time, leading to failure. But that hypothesis proved not to be correct. One of my fellow PhD students at the time was measuring pore pressure changes in long established cuttings in London clay, and she was finding that just over the time of her PhD, 3 to 5 years, that in some of the cuttings, the pore pressure was still steadily increasing. It hadn't reached its equilibrium value. Now, this is just an attempt to illustrate what happens when you make a cutting in a very low permeability, like London clay or Lias clay or some of the English clays, you're taking load off here. So when you take that load off here, you're inducing negative pore pressures down below here. So if you make the assumption that your pore pressure response is the same as that you would expect from this depth of excavation, and then you will get those blue lines there. In other words, your original water table will become the blue line there. You see that the pore pressure is dropping all the way along. It doesn't drop at all at the top there. That's why I've shown the original water table in there. But at the end of construction, if the thing is undrained and you're making a bit of a approximate assumption, because this is not there's this movement occurring in the horizontal as well as in the vertical direction. But if you make the assumption that the pore pressure change is just exactly what you would expect due to the weight of the soil being taken off, you get that blue line there. And then with time, you've obviously got a hydraulic gradient, and water will steadily move towards the cutting and eventually take up some new position, which I've just postulated there with that line as the final water table. And that was really the reason why many of the cuttings in the London clay were lasting for 5 years or 10 years or even longer and then failing. It was because it took that long for water to flow through London clay and rise to its equilibrium position. And as that process was occurring, of course, the shear strength was steadily declining, leading eventually to failure. Okay, next slide. I think we're getting near the end. Yeah, this is just a picture illustrating the changes. In other words, I think I used to give this as an exercise to my students to do, to actually work that out. We're looking at the top here at the vertical. This relates to one element of soil somewhere on the postulated slip surface. So it's a particular piece of soil. So when you take off the load above, your vertical stress decreases. And if we assume it's undrained, you will have no change in the effective stress making the cutting. So your total stress goes down, your pore pressure goes down, and your effective stress stays the same. From that point onwards, the water starts to seep towards the excavation and the effective stress is decreasing. So that's how your stresses change. And if you look at the pore pressure, when you take the weight off, your pore pressure drops down. That line will be, the blue line will be parallel to the brown line above and reaches a low value at the end of construction, from which point it steadily rises. And as it rises, your safety factor declines. And if you've got your sums wrong, it leads to failure. One more, please. Next slide. Yeah, that last slide, it was valid for low permeability clays. If you're talking about residual soils, they've often got a much higher permeability, well, many times much higher. So that picture in the previous slide is no longer valid. So I've tried to imagine something a bit more realistic. So if we look at the top one, that's the pore pressure one. Yes, as I've said, the dotted line is what you would have in a low permeability clay. But if it's a residual clay, it's much more likely that your pore pressure rises or changes almost as you take the the water seeps into it as you make the excavation, and then you'll have a situation where you have a seasonal change in the water pressure, and you'll have these blips on it. And these are the ones where you have these sudden short storms. The nice wavy line is the seasonal changes, and the pointed ones are what you have due to sudden storms. And those are the ones that normally cause the failures. We've had massive rainfall here in Auckland and other parts of New Zealand, so that there are many hundreds of slips all around the country at the moment. So I'll just read what I've read here. Short term, the end of construction, and long-term pore pressures and the stability of cut slopes in low permeability soils as I've just explained, and in moderate to high permeability soils. Next slide. And that brings me to the end. I did my PhD between 1972 and 1976. I then came back and worked for a consulting company, during which I had to go to London to be a witness in a contract dispute. It was over the construction of the dam in the island of Mauritius, and there were issues about unforeseen soil conditions. But while I was there, I rang up Bishop, and he invited me to come out and meet his wife. Bishop had always been a bachelor. He was still a bachelor when I was there, but he had quite a serious mental breakdown, and it was due to the results of some pills he was taking for mild depression, and the pills had a bad effect on him, and he had a breakdown, and he never went back to Imperial College, but he recovered from the breakdown quite well. And then his specialist told him that he should take up something other than just returning to his old life as a professor of soil mechanics. And he found out that Bishop didn't drive a car, so he suggested to Bishop that he should learn to drive a car. And so Bishop he was only in hospital undergoing treatment for about 3 months, I think. His family, the Bishop family, had been very friendly with the family whose daughter was Myrtle. She had married, but she was a widow, and she knew Bishop, and she knew he'd been ill, and she knew he was learning to drive a car, and she offered to help him learn to drive a car, which she did, and he learned to drive a car. And I got a letter from Professor Vaughan, well-known professor at Imperial College, I think in about 1981 or 82, I think. He said in his letter, you might like to sit down before you read the next page. And on the next page, he said, you will be surprised to learn that Bishop has A, learnt to drive a car, B, got married, C, lost all interest in soil mechanics. So when I rang Bishop, this was in 1986, I've put it there, 1986. He said, oh, you must come out and visit us. He lived in Whitstable on the edge of the Thames estuary. I got the train to Canterbury, and he picked me up at the Canterbury station, and we drove around Canterbury, and we walked through the cathedral, and he took me home to meet his wife, and we talked about all sorts of things. It was really nice to meet him because he was really in very good health and enjoying being married. And as Peter Vaughan warned, we didn't even mention soil mechanics all of the time I was there. And it was only 2 years later he had a heart condition from a way back, which was partly why he was taking pills, because the doctors didn't want him to be anxious about things. But they decided that it was precarious, and they did an operation on him in 1986. He recovered from it, but 2 or 3 days, there must have been something went wrong, and anyhow, he died in 1988, and I got a message from Myrtle to tell me about that. So I think that is definitely the end of my presentation. I'm quite happy to hear comments or answer questions. And thank you all for listening. If you are still listening, thank you for surviving right through. It's a bit long, but anyhow, there it is.
Thank you very much for the presentation, Professor Wesley. I have some questions regarding the life of Professor Bishop mainly. How many years did you work with him? Maybe 3, 4?
I worked with him for 3 years exactly, because he only had money to employ me for 3 years. So I had to finish my PhD in 3 years, yeah. And I was very lucky that my apparatus worked so well, you see, and Bishop wrote a paper on it, and it got marketed, you see, and they are still using it.
They're still using it in Imperial.
Yes, 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 at Imperial, yes, yeah.
And how was your relationship with him? He as an advisor, how was he as an advisor?
Oh, he was, well, it was interesting, but because of the pills, he was already starting to suffer the effects of the pills, because he wasn't as, well, just over the 3 years I was there, he wasn't as interested in my results at the end of my 3 years as he was at the beginning. So he was starting to lose interest. I was his second to last PhD student. His last PhD student was David Height, actually. And David Height worked with him on what they call the hollow cylinder apparatus. And that was David Height was his last full-time student. I was perhaps his second to last one. No, we had a very happy relationship, really. And I think
he
I
was
was
working in the lab, or he was in his office, or he was in the lab all the time, Dr. Bishop?
His office was across the corridor from the laboratory. What he used to do quite often was, when everybody had mostly gone home, he would go into the laboratory and inspect the apparatus his students were using or what they were doing. And if he didn't like it, he would just tell them very gently the following morning that he thought what they were doing was needed to be improved. People told me when I started, don't expect Bishop to come up with the design. If he expects you to do it, you've got to do it. And you'll just have to keep trying until you get his approval. So that was exactly how it was. I wasn't very happy having the load coming from above. When I had it coming from the bottom, I thought it was quite clever, actually. And Bishop agreed. He said, "Oh, very quickly, I'll get it, draw it all up, and we'll get the workshop to make it." And it worked very well. And also, he had samples from a test pit out on site. He had samples, I think, about 24 centimeters in diameter in large tubes. He had about 30 samples, and the triaxial sample is only very small. So I said to Bishop, our results would be much better if we did several tests, several identical tests at each time. He thought it was a very good idea, so he had another 3 of my cells made. So I always had 4 cells doing identical tests, not always, because some of the tests were very long term, but most of my tests I was doing 4 samples. I would prepare my samples in the morning. I would arrive, and my tests usually ran overnight. I had a recording equipment. So the first thing was to take apart the 4 cells, and the next thing was to prepare another 4 samples, put them in the apparatus and set them going and leave them running for 24 hours. Those were a lot of my tests, but a lot of my tests were on different types of tests and things like that. But I will have the record for all time for the greatest number of tests done by a PhD student, if that's of any interest.
Definitely.
Yeah,
And
I was quite pleased with myself, because you would think, I was married at the time with 4 children, and you would think a student married with 4 children would have less time than undergraduates coming straight through who are bachelors, would have more time, would have less time than they did. But I finished my PhD in 3 years, whereas most of the other ones were taking 4 years or 5 years, quite a lot longer. So I had to finish in time, or I wouldn't have had any income, you see. So there was quite an incentive to finish in time. But I had a very good relationship with Bishop.
Also the issue that you were married at the time with 4 children.
Correct.
There is when you have you have 4 children, you have to organize very well with
Correct.
work and family to
Correct.
because it's demanding,
So,
right? It's there is a lot of
that's
demand,
right.
and inevitably you grow up, you mature faster when you are put in
Yes,
such a situation.
true. Yeah. So every day I would come home, I would have evening meal with my children, and then at one end of the lounge there was a big table, and there was a TV. So Barbara and the children would watch the TV while I processed my results and do my graphs on the table. You see, so we were still one family, and they were watching the TV, and I was drawing my graphs. And in those days, it was all manual work. I had ink and pens and things to do all the drawings by hand.
I see.
And it wasn't like you can do it today in front of a
I
computer.
see.
It was quite different here. And
So
the system too was I got from the recording device, I got a long strip of paper which I had to then manually just read the pieces off to draw the graphs, or to process it. Really, it wasn't automatically processed by a computer program.
I see.
Anyhow, it was a wonderful time. It was a wonderful time. It was very
I'm sure. I'm sure. I'm very. I mean, it was also a very challenging time because the effective stress, based on what you showed us, it was quite new, the way to understand it at the time. So you had to from the perspective of the triaxial, right? Because there was
Yes.
a clear idea based on what Terzaghi did on what
Yes.
effective
Yes.
stress were,
Yeah.
but somehow you had to also put it in the ground with a formal procedure to work around it, and that's
Yes.
the main legacy probably of
Yeah.
Dr. Bishop and on all his students who work on the triaxial in different
That's right.
regions, right?
I should tell you about my my oral. You know, when you do a PhD, you have an oral examination, and Bishop had invited Peter Roth, Professor Roth from Imperial College, to be the other examiner, which turned out not to be a very good choice, actually, because Peter Roth was a very firm believer in critical state soil mechanics, and Bishop wasn't. But the first question Peter Roth asked me was, how many technicians did you have working for you to do all of that testing? I said, I did every test myself. And Peter Roth looked rather skeptical. But Bishop spoke up and said, yes, Laurie is very capable. He not only designed the apparatus, but he did more tests than any other PhD students have ever done before. So, and then Peter Roth asked a few more questions, and it was quite tense, really, because he was trying to find out how much I knew about critical state soil mechanics. But eventually they said, after about 2 hours, would I like to ask them a question? So I said, yes, what did you think of my Poisson's ratio values? I thought they were quite low. They both looked totally blank, and they sort of muttered around and tried to think of something to say. And then that just about brought it to the end. But they passed me. I went out and they conferred, and then they came out and said, oh, you were passed. And Bishop said, Wesley had a problem with his interview because neither of his examiners had really read his PhD thesis, which was true, you see, because when I asked them about the Poisson's ratio, neither of them had read that part of my thesis. Anyhow, they passed me anyway. And that
That's
was the
very
end of
good.
the matter. Yeah.
I see, but it was you were nervous at the time.
Yeah, I was very nervous. And one of the Eileen was the tea and the coffee lady. She bought some coffee and biscuits in halfway through the oral examination, and she went out and told them outside that the atmosphere was very tense, and so anyhow,
Very nice. Very
I
nice.
had to wait about
Thanks for
I had
sharing
to
those
wait
details.
about 10 minutes. They sent me out and I waited about 10 minutes. And then they came out and congratulated me and said that I had my PhD.
That's a wonderful
You have
moment,
probably,
right? That's a
yeah,
wonderful
it was.
moment.
Yeah, exactly. Yeah. Yeah.
So, Professor, I have another question. Do you remember any anecdote with Dr. Bishop or any anecdote of Dr. Bishop with someone else, maybe?
Yes, I will tell you one anecdote. It's not mine. It's from Eddie Bromhead. He was there during I'm not sure whether it was the MSc or the PhD course, but Eddie Bromhead was there and he had a very bad headache and he wanted to get some pills for his headache. Now, Bishop's secretary's name was, what was her name? I forget, but she was very attractive and all of the students were in love with her. But Eddie, he went and asked her if she had any pills because he had a bad headache. She said no, but Bishop is sure to have some pills. Just ask him. And he was rather reluctant to ask Bishop, but he asked Bishop and he sat down and Bishop said, "Oh, sit down." And so Bishop gave him about a 20-minute lecture on all the causes of headaches and gave him so many different pills to take that he almost had his briefcase full of little bottles of pills when he left the Bishop's
I see.
office. So Bishop was known as a hypochondriac, that he would talk for ages about his various ailments. Unfortunately, that it was true that he had a bad heart. Yes, they had diagnosed that when he was quite young, and that was one of this is an interesting point. One of the reasons there was bad feeling between Cambridge and Imperial College was because the head of the soil mechanics team at Cambridge was Roscoe. And Roscoe went to war. He was enlisted and served in the war. But neither Skempton nor Bishop went to war. Skempton managed to get himself classified as essential person, but Skempton had the right connections. And Bishop failed on health reasons. He would not go because he was a Quaker, and the Quakers don't believe in taking part in wars. So neither Skempton nor Bishop went to war. Roscoe got captured in the early years of the war. He spent about 4 or 5 years in prisoner of war camps. And there was ill feeling that he did his served his country by going to war, while Skempton used his connections to not go to war. But
Wow.
that's the long history thing. Yeah. Yeah.
Wow. I didn't know that. I didn't know that. Very interesting. Very interesting. I didn't know that
Yeah,
about Professor
that's right.
Skelton.
Yes. And
Wow.
Skempton, Bishop used to say, well, here at Imperial College, we do our research so we can solve practical problems. We know a lot of practical issues and we do our research to answer the issues. Cambridge, on the other hand, they've already got their solution. They're just looking for problems to solve with critical state soil mechanics. That was Bishop's short view about critical state soil mechanics, that they had a very nice theoretical formulation. But in Bishop's view, you see, I was at a seminar at the University of Laval in Quebec. I was on my way to the conference in Montreal, the international conference. It was a 2-day seminar, in the course of which the speakers were Bishop, Skempton, Roscoe, and Rowe. Roscoe did his presentation on critical state, and he showed, quite rightly, the sort of graphs you get with sand, how if you start with a loose state or a dense state, you will end up on the same failure line with strain still going up, but your volume change and your strength constant. And Bishop, when it came to the discussion, Bishop said, yeah, that's all very well, but if you do a test on a clay, particularly an undisturbed clay, you will never get failure like that. It will always failure on a failure line, and the strength will decline from the peak strength to the residual strength. And Roscoe said, yeah, we know that, Alan. I'm talking about sand. So Roscoe at least recognized early on that the critical state was very difficult to apply to clay because you can't create the critical state in the clay, even if you continue your test for quite a long time. It will pass from the peak state to the residual state, and you won't know where the critical state value actually is. Even in compacted clays, we tried this out on some compacted clays for a different reason. But you get them appearing to fail as if they're failing just by bulging, but still they fail on particular failure planes. So you have great difficulty in creating the failure state in a clay, in an undisturbed clay. You can do it with the molded clays to some extent, but so that was Bishop's arguments against critical state.
Very nice. Thank you very much for sharing all of those details, Dr.
It's a pleasure. You're very welcome.
Thank you very, very much.
It's a pleasure.
Okay, for the sake of time, I wouldn't like to take more of your time. We have been a long time already talking, and you have a beautiful day ahead, I am sure of. So I only have words of appreciation, and thank you very much for sharing all of this. We really learned a lot about the life of Dr. Bishop. It was also a very nice instance to see some of the most important concepts related to the behavior of soils in general. The undrained, drain conditions are vital when it comes to design. So, right. and the proper understanding, regardless of if it's whether a clay or a sand, I mean, it's important to understand failure criteria and design analysis and design True. Assumptions, right? Soils are way more than C and Phi, and right. That's an eternal discussion that the people who love soil mechanics will have.
Right. Okay, look, no, you're very welcome to distribute that PowerPoint. You can give it away and use it. I think actually I've got a written hard copy of it. I will send it to you. But right. You're welcome. You can welcome to, and I'll send you the hard copy. I think I can find it all right, and you can give it away and do what you like with it. There's no constraints.
That will be great, Professor. All right.
Thank you all for listening.
Of course, no, thank you for all these great details and geotechnical engineering and all this beautiful discussion, and also for sharing some details of the life of Dr. Bishop that not everyone knows. Right. So it's always very nice to learn about the person beyond the legend.
Exactly.